Hello everyone and welcome back to this course. So last class we are discussing about the bipolar plates and their desired properties. So let's continue discussing on the materials now. So commonly used materials for bipolar plates are basically first very preferred is graphite. Primarily because it satisfies all the properties that are desired or possessed by bipolar plate. So satisfies all important properties. So where it basically falls short is primarily issues with the graphites are it's a poor manufacturing. As we understand, graphite is a very brittle material, so manufacturing those channels on the graphite plate is a slightly tedious task. Cost is also an issue, and third one is the strength. Strength is also not very much in case of graphite, and that is why steels are very likely used. Let me write, steels are preferred. Stainless steels primarily because of better fabrication ability and this much better mechanical strength. Since steels have got good mechanical strength, we can even reduce the thickness of this bipolar plates, and that is why we can even reduce the thickness of the entire stack, or size of the stack can be reduced. Even the gravimetric and volumetric power density of this stack can be enhanced very considerably. Now, what is the issue with the metals is basically they are very prone to corrosion. So, let me write this up. However, metals are prone to corrosion, and this corrosion which takes place on the surface of bipolar plate, typically where the gas diffusion layer touches the bipolar plate, that is the layer, that is the interface where corrosion is can be observed, and this oxide layer that is formed on the surface of this bipolar plate is highly insulating in nature, and that is why the entire, as we can see, the resistance of the cell or the stack increases drastically if this corrosion is not addressed properly. So that is why we need to have anti-corrosive coatings, such as we have lot of options available. Titanium nitride is there, or chromium nitride is there, or even literature you can find platinum coating or gold coatings are also being used for this anti-corrosive coatings. Now let us quickly go through the patterns that are basically used. So let me write patterns. So these patterns are the ones that basically define how a reactant species or even the product species will flow over the gas diffusion layer. So we have mainly three, we will discuss three patterns. So first is your parallel flow. So patterns basically define how species are going to flow over gas diffusion layer, or once the water is produced on the cathode side of fuel cell, how it comes out and how it is going to flow out of the fuel cell, that also is very well defined by these patterns. So let us talk about the parallel flow first. Let me draw how it looks like. So when we have a bipolar plate, so let us say this is the inlet of the species, that is where they mark their entry. So parallel flow means we have channels that are parallel to each other. So these are the channels. So they are very parallel to each other, and they are also equally spaced between in this entire area of the electrode. So this distance between two channels, let's say it is d. D is same for all the channels, and this is the width of the bipolar plate, and this is where they come out. So this is a exit and this is a entry. It can be little on this side as well. So as we can see, as and when this hydrogen, let's talk about hydrogen. So as and when it enters, it starts flowing through these channels and it reaches the the exit of this flow field design, and then that's how the entire electrode area is covered. So what are the advantages of such design? Since all the channels are parallel to each other and the flow also happens simultaneously, that is why this design is called as parallel flow design. So first and very promising advantage that we get in case of parallel flow is the very reduced pressure drop. So in other words, when the hydrogen or any other reactant species that flows through these channels, we don't observe any huge pressure drop as in from when it travels from entry to exit. And second one is very simple in construction. Which ultimately leads to the lower manufacturing cost. So this is one of the these are the advantages of the parallel flow design. What are the issues? Issues are the first one is the flow distribution may not be uniform. So this is particularly when width of bipolar plate is more. So what basically happens is, since we have parallel flow for the species, let's say if the water gets produced and it gets stuck in this one of these channels, that particular channel is completely avoided by the reactant species, and the reactant species basically they flow from the other channels. So that is why this flow distribution will not or may not be uniform across the electrode area if we have any hindrance to the flow of channels, flow of species in these channels. So second one is particularly in case of fuel cell. Early in case of fuel cell, when water is produced, its distribution may not be uniform. And where does that lead to? That leads to more mass transfer losses. In other words, if we have water produced from on the cathode side in case of hydrogen oxygen fuel cell, we can see that if this water gets stuck any of the channels, that particular channel becomes useless for oxygen to flow. And in other words, when the oxygen gets stuck or when it is not supplied to the reaction sites, it basically means that we have mass transfer losses popping up, and that is the main issue with the parallel flow. Second one is the very famous serpentine design. Let me draw how it looks like. So let me first draw a single channel. So there is only one channel in this particular design. So this is the entry point and this is the exit point. So as we can see, the species basically will flow only through one channel. There are no other channels for the species to pass through, and that is why the species force each other, the other species, the other molecules, other particles to flow through this thing, and that is why the flow is better in this kind of designs. Let's quickly draw. This is a single channel. So let me write single channel design. How does a multi-channel design look like? So I'm going to use different colors. So let me start with, so I'll draw 3-channel design. So this is one, this is second channel, and this is the third channel. So I've completed one channel. Let me complete the second channel. And third channel. Right, so this is the entry point for hydrogen, or as an example as an hydrogen here, this is the exit, this is the entry, this is the, you can say, the entire bipolar plate. This is multi-channel. So I have shown here is an example 3 channels. We can have a 5-channel design, we can also have 10-channel designs depending upon the size of the bipolar plate. This is multi-channel serpentine. Flow field pattern. So what are the advantages here? Let me also write, this is the most commonly used design. Or flow design. Now what are the reasons? Reason is, first, it can very well take the water out of fuel cell. Now why is it so? As I have mentioned earlier, there are dedicated channels. So as you can see, one channel is not connected to the other channel. So whenever we have any water produced and it is taken to one particular channel, the species that are flowing through that channel will force that water to flush out, and that is why this kind of designs are very preferred for water management in case of fuel cell. So let me write as each channel has dedicated pathway. What are the issues? First one is the size. As the size of electrode increases, the design faces higher pressure drop. Why is it so? Because if you see, all these species, they are forced to flow through dedicated channels. They don't have any other way to move out, and that is why there is a huge pressure drop as and when the species travel. But this is particularly towards the end of the channels, or from the middle of towards the end, we can face a more pressure drop. Third one, interdigitated interdigitated design. So let's write, let me draw this first. So when we have, let's say this is the inlet. So what we have here is channels. The inlet channels are all connected. However, if you look at the exit channels are, they are basically not connected to the inlet channels. So this is the entry. So if in case of hydrogen flow, it flows through like this, and while it flows through these channels, it basically through diffusion layer it travels to the exit channels. So through diffusion layer it basically travels to the exit channels. I'll also show how it so if I try to show through, this is, let's say, the bipolar plate, and these are the, this is your diffusion layer and the electrode, and this is the electrolyte. So we have, this is diffusion layer and this is our bipolar plate. So when we have, let's say, hydrogen here through these channels, so this hydrogen basically is forced to flow to the other channel through the diffusion layer, as it has no other way to reach the other channel. As we can see here on the figure on the left, the entry and exit channels are not connected directly. So there is a space in between, and since we have inflow, in order to have the exit flow, we should have this hydrogen flowing from inlet channels to the exit channels, and that is the only way possible. Is this flow of this hydrogen should happen through the diffusion layer. So there is a convective flow of hydrogen or the other species of interest through this diffusion layer, and that is what makes this design very special. So let's write quickly what the advantage is. So first one is we experience forced convection in GDL, which reduces the diffusion layer thickness. We have discussed this before. This is denoted by delta. So as our delta decreases, what happens? That leads to increase in the limiting current density. So this limiting current density increases. Second one, so we have a better water management as well, as the water is basically forced to flow through diffusion layer out, and it is forced to basically enter the exit channels, and that's how the water is also taken out. So we have a better water management, and where does this lead to? This leads to again increase in the limiting current density as our concentration losses decrease. Or mass transport is basically effective here in case of this design. Let me write. mass transport is effective in this design. So, what are the issues? First one, as we can see, as the reactant and product species are basically forced to flow through the GDL. So, as we have seen this, that this reactant species or even the product species, they are forced to flow through this GDL. So, what happens here? So, the design experiences very high pressure draws. So, in other words, we need a very high energy in terms of pressure energy to basically force this species to flow through this GDL and through these channels which are not connected to each other. So, we will stop here and we will take on with the scale up issues in the upcoming sessions. Thank you.